Hey, Luca.
Hey, Thomas, how are you doing?
Well, pretty busy week, but
Yeah,
good.
yeah. I hear you were busy with a very large model.
Oh, yeah, that might have been the R1 that told you.
Yeah, that's very exciting, and it's always good to push the boundary. Now, hopefully in 2 Fridays nobody will come up with a 1.5 trillion parameter model, but
Yeah, I
by
mean,
now we kind of understand the recipe, right?
after R1, we will have R2, and then it's R2D2, our
Yeah.
favorite guy.
Yeah, that's good. So after the dead joke, I would think that we have to rehash the what we did the last time. So the last time we walked you through the interpreter.py, which is this crazy project where we implemented a Python interpreter in Python to be able to basically control how we interpret the whole computation from the bytecode to whatever it's executing. And we created an example with manipulating strings or having string operation or string as a data type. And we created a proxy for a string, which is the object that we understand. And then we can reason about and, enrich with more information as we interpret. Um, and why we did string, because it's different enough from tensors, just to demonstrate it's a general mechanism. We have also wild ideas for how we may use the interpreter in the future, but today we're gonna go back to tensor land. And so we're gonna see something about string and then see how we're using the interpreter in Thunder to generate the trace. And so we'll get a bit of detail of that part. Yeah. So do you want to, Thomas? Do you want to share
Yeah,
your
I'm
your
on it,
screen?
but it's not easy to share the screen.
Oh,
Okay,
here. Yeah.
so here we are in our favorite development environment, of course, this Lightning Studios.
Of course.
Um, and here we are with the function from last time. It's not like really creative, but good enough for me. And then we take the interpreter, and what we had here was a string proxy class that filled in for strings, but it had the ability here that it behaves totally like string because it inherits it. But you could be using print, and then it would optionally like print the variable name or the argument that it came from, or if it was a constant, it was printing const. Um, and then we had this callback for wrapping a value, which is called whenever Python sees a value for the very first time, or our Python interpreter sees a value for the very first time. And then we had a string add lookaside, and we had lookasides like all over during the course of the Thunder sessions last year a number of times. It's the method to say if you encounter a call to this function, call that function instead. And so we did this for the add lookaside, and then we had this lookaside lookup function that essentially does this dispatching. And under the hood, because here's the default lookaside, this handles things like dictionaries and lists and tuples and other things. Um, so here we have that. And then we ran this interpreter, and this returned a function. And when we call this function, this will be ran in the interpreter with the lookasides, with the substituting the values for the proxy values when it sees a string here. I added two things. I added here an equality method on the string proxy class, and I added that we record the return operation in the list of operations. And so what happens now if I like call it, it records all the operations I do on the string, and it produces a straight line program here, like the trace.
Looks like a trace. Yeah.
Yeah. So basically, from the if condition, we assert which part of the control flow we took. So we assert that this was true, and it's encoded here. And then you have like the computation of the result, and you return the result. And if
So
I
this
call,
basically, yeah, go ahead.
yeah, no, you say.
No, this basically will has generated a function in Python that captures the flow of the function with the inputs that we originally applied to it. And so it's a straight line program that is easy to reason on, but it's conditioned on the fact that the inputs are actually compatible with the branching that the program took during the tracing. Yeah.
Yeah. And of course, if you want to build this into an interpreter, you could, for example, if you're okay with having a different program whenever the control flow changes, you can condition the caching on it as long as you can reason. So
yeah, and just one thing, just one thing to add maybe is that this avoids us going back to the interpreter, but there's nothing that prevents us to do other things with the interpreter, right? You could always go through the interpreter if your function is not very complex and you don't care about it not being super fast. Then you could like trace and retrace every time and look aside whatever you want. The point here is that we are kind of freezing the control flows because the ultimate goal is to create a function that doesn't depend on the interpreter, then that can be run as fast as possible. And manipulated and so on. So this is why we're asserting on the input. There's nothing fundamental. It just avoids us going back to the interpreter and say, can you interpret this section because I don't know what's going to happen.
Right. And so the other part here that you can see is we used strings as the representation for the operations. Of course, the Thunder traces are more structured, so you facilitate manipulation. But so if I run the same thing through the interpreter with a different input, it will now assert like the opposite condition. So it doesn't check the name itself, but it only checks whether the condition evaluated to true or not.
And it takes, sorry, I'm interrupting, but you're going through very tricky things, I think, for whoever looks at this for the first time. Like, I think that we need to understand that this condition automatically derives from the if condition of the function it's being traced. So it's a comparison operation that happens to happen in the function there, like if s equal Luca there. And that, since it's a comparison operation, and that has, that lives in at some point of a branching control flow, it gets captured during tracing, and this is where we automatically generate the assert for it.
Yes.
And yeah, this is how we know if the program might be valid or not.
Yeah, and so what happens here is that it runs through the equality operator here, and this checks if the other thing is a string proxy too, and if the type is not constant for both of them, and then it inserts this assert. Quite likely, I could also handle the case where B is not a string proxy, but proper string, and then just do something differently. But so this is the gist of how this is created. And you need this always at the boundary of the logic that you capture, right? So here is the casting to the comparison and making a Boolean out of that, and we don't track Booleans. And to proxy the Booleans is actually pretty tricky because Python requires things to return true bools and not bool proxies from calling bool, and that is precisely to evaluate the control flow like this. Yeah. And so this is what happens here.
And then we can hoist all these things. Like if we had a long code and we intercepted all the conditions that happen throughout the function, we can take those conditions and hoist them to at the beginning, right? So we can then inform a caching mechanism on the validity of what we acquire.
Yeah.
Potentially.
And I mean, to the other at the other end, you have that if you go here to a Boolean value, and so if you do a comparison of tensors, for example, you get a tensor with the comparison value. But if you then cast that to bool, it will be like a Python Boolean afterwards and no tensor anymore. And this is like the classical data-dependent control flow that we and most other deep learning compilers like have trouble with. And so this is kind of a bit interesting also in this regard. But so that is as it is. And this is like how it works for this tiny toy interpreter. But of course, the mechanism is not that different for the like proper Thunder JIT, which builds on top of the interpreter, just like our toy JIT. And it uses the same mechanisms. Like it has the wrap callback that replaces objects of interest with proxies. It has it uses proxy classes for tensors and also to some extent for numbers if that's needed. And then it also uses lookasides a lot in order to like redirect calls into Torch to calls into Thunder Torch.
Yeah, and we want to now, we talked about proxies, right? And so going back to Tensor World or TensorLand, we do treat we deal with tensors, of course, in your original program, and we turn them into proxy tensors, just like we took strings and we convert them to proxy strings because we need a richer object, but not just that. Not like with strings, we enriched things. With tensors, we do something else than just enriching. And so I'm going to draw a couple of diagrams here just to inform the next step of what we're going to show, which is like what happens in the JIT in Thunder. So what is a tensor? A tensor is a storage of numbers. It's usually just, storage that, can be like differently shaped, but usually doesn't necessarily have the shape of the tensor. Like it's not a physical array of things in memory. But what makes it an array is tries, sizes, or shape, as NumPy calls it, and also at some point Torch decided to call them, and then dtype. And these are the main ones.
Device.
Oh yeah, of course, device. Dtype is the numerical type, so float 32, b float 16, float 8, whatever. Device is what device is running on, and PyTorch makes it very explicit. Other frameworks make it a little bit more implicit, like JOX doesn't really like you to mess with the device at the code level, but it will kind of delegate to XLA whatever device it will end up using and so on. With PyTorch has a very explicit treatment of those. So in creating a proxy tensor, which is what we need to represent in the trace, right? What the whole business of creating a proxy tensor is that we can it's something that we can reason about in a trace. And we don't actually want to capture all these things for strings before we had the actual string, the characters in the string, which is the value. And then we could assert the value to be equal and so on. And here we'll still assert certain things because at acquisition time, the example inputs will have certain values. And so at compile time, we can say, okay, this is, contains all ones, but so that we can know if inputs will change in the future, or the metadata will change. So we can do all sorts of things, but what we capture in the trace is actually a subset of these information. And typically it's this guys here. Um, I'm putting a dotted line here because we may capture strides in the future, and we can talk about strides in a separate episode. But essentially, is how large, like what is the dimensions, and what is the shape? So is it I don't know, 254, 224, 224, and then I don't know, three whatever tensor, and then the batch size 10. Okay, so this is like how large across each dimension and how many dimensions the tensor will have, and then the D type and the device. And these three pieces of information are enough to be captured in the proxy tensor for us to capture the computation, because we can say, okay, whenever there is a torch add that needs to execute, this torch add operation will take two arguments. And the arguments will have these properties like D type, device, and size. And this will define the operation because it will cleanly map to something that is CUDA kernel, for example, that will run. Now, the CUDA kernel is not really interested in what values are in the storage. So is there a 1 or a 0 or a 3 as numbers of the tensor? But it's interested at understanding what is the shape, how many dimensions, what is the shape, how can I slice up this thing to run it in parallel.
At least the administrative parts of the CUDA kernel, right?
Yeah, for sure. The administrator, knowing which one
the data.
Run. Exactly. And so you can have, you will have many operations that operate on many things that in the Thunder trace are represented by proxy tensors, which have these three properties and represent them. And one way you can relate to what PyTorch has is the meta device. So if you allocate a tensor on a meta device, instead of saying CUDA 0 when you say device, you can say device equals meta, which will not instantiate the tensor in the storage. We will keep it not allocated, but it will characterize the tensor as a thing that has a certain shape, a certain D type, and a certain, device will be meta, and you will assign it to be a concrete device later on. But that already allows PyTorch to reason about what happens to computations in general. And this has the side effect that you could trace R1, as we were saying at the beginning, right? The 600 billion, you could trace it on your laptop and represent the whole computation on your laptop. You don't even need a GPU to understand the sequence of things that will happen or transport it or even distribute it. This has the added value of, I can trace it on something that doesn't have enough memory to hold it, but then I can chop it up and then make it concrete with actual numbers in it once I distribute it. Right.
Obviously, you would need that for distributed if you have something that doesn't fit in the memory in the first place, right?
Exactly. So let's take a look at how this is done in practice within Thunder when we talk about tensors and tensor proxies.
Yeah. So let's share the screen again. And I should have some practice now, right? So if we look at the...
you should train an agent to do this.
Yeah, right. If we look at the core directory from Thunder, you have the JIT, of course, here. And it's called JITExt for historical reasons. But so you have the same thing here that you have that we discussed, that you have various, let me find this, look-asides, and you have the rep callback. And so this is quite, now it's my using GitHub, right? So we have a thing where we transform things to proxies. It's a bit more detailed, but basically somewhere in here there will be just proxify call also here for tensors, right? We always want to proxify them. And then the tensor will be swapped out for the proxy for the remainder of the computation, and it will maintain this link. And one of the things that may happen is that if there's something unforeseen happening, like you call a function that suddenly gets a tensor proxy instead of a tensor because there's no look aside for it, this will be the typical error message. Like, I was looking for a tensor, but I got a tensor proxy. That is when we substitute things here, and then Python like topples over. And so this is the callback, and then there's the look aside function. I'm not sure that I find it right now.
Yeah, and you basically, this file is primarily how you, the data structure, the proxification of tensors, then the data structure that holds the trace, just like we did on string, a bit more
right.
Elaborated, and then a lot of look asides.
Right, and so here we have a more elaborate look aside function, and in particular, it has a map of functions that things get automatically registered in. Or if you have a executor that has this replaces, like we did for the matmul, or for the relo matmul, or not for that, but for the, I think the RMS norm we did it, right?
Yeah.
But so if you register a look aside, an operator that has a replaces something attribute, then this will be in the executor look asides. And so there will be a lot of look asides here, and we have, of course, things built in there. And so this is basically where all the mechanics of the translation are, and there's also things like autograph functions, whatnot. And then we, of course, need to know what to look aside to. So we have a torch add, and now we want to look aside. And this is, we've not only implemented our own version of Python, of the Python interpreter, but we also have here an implementation of all the torch functions, or something that looks almost like it. So if we take, for example, add, do we have add here? Yeah. So here's the add that we have. And so one thing here is that it's a function, and it has about the same signature as torch add, except that it probably takes a few more numbers. You could probably pass all numbers for this. But so it can take tensor proxies, and it will then call into another thing that is called clang add, which is like the less abstract mapping, but there's an intermediate mapping layer. And then it is decorated with the torch symbol, and this here says, I'm a thing that replaces torch add, and also torch tensor add, which is like similar, but it's not quite the same. And so,
yeah, maybe a comment that we can add is that since we were talking like what we just said, right, with tensor proxies, they don't contain the numbers. And so what that line 1953 does is calling if alpha, it could be a tensor or not a tensor, yeah, whatever it is. But what all these lines do, even including the clang add AB, is not executing that operation. It's evaluating what happens to whatever tensor proxy has in it, which is size, dtype, and device.
Yeah.
And so
if you remember implementing our own operations and executors and registering them with the executors, so this is the equivalent of a meta function, right?
Exactly. So we'll change the shape of a tensor? Well, surprisingly, yes, because it could be, there could be broadcasts and so on going on, right?
Yeah, I mean, we could trace it to the Clang ad if we want to. Um, but yeah, there's
No, it's fine.
more
Yeah,
and more operations in here.
yeah, yeah, yeah.
And then once we have this, and this is a bit different to how the custom operators work, but in the end, it's not that different. There are executors that then say, well, I can execute this symbol, which is like our name for the operators that we can put into traces, right?
Yep.
And so this is basically what's going on under the hood when you run your PyTorch model through the Python interpreter. It will like redirect everything, ask the JIT component, like, here's a function call, what do you want to do with it? And then the JIT will say, yeah, don't execute it directly, call this meta function instead, or proxy function, which is
Yeah,
a meta function.
exactly. So there's no monkey patching going around, right? So it's not that we're swapping values for other values. It's
No,
more like we interpret and we say, okay, this is this input. We construct new inputs for the function that we interpreted. So we turn it from a tensor into a tensor proxy, and then we can do whatever. In this case, record what's going on as an operation, and also intercept comparison operations and Boolean operations, and do the thing that we were doing with the string. So hoist all these conditions to say, okay, this program is valid if this Boolean operation has this return value, because otherwise it may be a different branch. But I think the beauty of this is it's very complex in practice. It's very hard to build a Python interpreter. But the point is that once you've done that, it's extremely simple conceptually. And so, it's very clean and it sets itself up to be robust. Now, of course, before having a completely robust Python interpreter, it takes a while because you need to hit all the edge cases and so on. And also generating error messages that make sense, it's also a hard problem. So whoever wants to get in there and maybe fix something that comes up, absolutely. But the final point for this was and is already, bar some corner cases, something that doesn't need like too much magic. It's very, very linear. The process is fairly linear. So we wanted to share this with you because it's if you will, if the entry point both to understanding what's happening under the hood and also to fix bugs if they come up, and add new models, because new models will have some certain code paths, and how do I really understand how I can contribute by adding a new model that has certain things that are not supported? How do I interpret like the errors that come out of it? So that's the state that we're at.
So that's basically the story of the front end that we have here, where we go from the PyTorch program to our first trace, that then the transforms that we've seen over the last year and this year too, that those can operate on, right? But so this
Exactly.
acquisition of the initial trace, it does have quite a few components, and actually it is one of the bits that is our second attempt. And you need something, and the gist here is that like just using proxies is not quite enough, because you also want to have a control over the functions. And this makes us have this Python interpreter that also gives us control over the execution.
Exactly. Okay. So this is the finest level of the sausage. It was the sausage inside the sausage, the meta sausage. So hopefully this is completes the picture. of how things work internally, and it's not the whole story, of course, because there are other things, and there's how our transform is conceived and where it happens exactly. So we talked often about like pre-prologue and so on. I think we'll put things in order in the future so that they get more decodable, and everything will end up in the new README and the new docs that are coming. So very exciting.
Awesome.
Thank you, Thomas.
Yeah,
hope
thanks,
you
Luca.
have a nice weekend.
You too, Luca. See you.
Bye, everyone. Bye.